We defined physics a few minutes ago as the study of energy and the study of matter and the interaction between the two. And we talked about lots of different aspects of physics, from mechanics that we focus on primarily in Physics 20 and in Science 10, through electricity and magnetism, and even atomic physics, transitions of electrons that take place in the atom in Physics 30. This unit, the unit that we're going to start Physics 20 off with, is called kinematics. Kinematics is a study of motion, but it's a study of motion without regard, in other words, without paying any attention to whatsoever what causes that motion. In other words, we're not going to look at forces at all in this unit. Forces cause motion, and we'll look at those, but not right now. Okay, that's for another day. We're going to look at motion, the motion itself, not the thing that causes that motion. Now we're going to define two terms that kind of lead us into this whole kinematics thing, a vector and a scalar. And these are two terms that you've probably seen before in Science 10. You may or may not remember what each of them is. Does anybody remember what a vector is versus a scalar, say? You guys learned this in Science 10, right? What's the difference between a vector, starts with a V, okay, and a scalar, starts with an S? Okay, two examples kind of go nicely along with that, right? V and S. Yeah, go ahead. Good. A vector has both magnitude and direction, so it's a quantity. So it's a measurement, a quantity, a force, a velocity, a speed, a acceleration, something, a quantity with both magnitude and direction. And a scalar is a quantity that has only what? Yeah, it has only magnitude. So there is no direction associated with a scalar. And there's lots of examples of quantities that have both magnitude and direction, where direction matters. But then there's lots of quantities that don't have any association with direction, where the magnitude doesn't matter, or the direction, I should say, doesn't matter. If you're driving to Edmonton, the direction matters. If you ask what the temperature is, the direction doesn't matter. There is no direction, right? Okay, if somebody says, which way is the sky? You're going to say up. Direction matters, right? If somebody says, how heavy are you? You're going to say, I weigh 150. There is no direction associated with that. So sometimes direction matters when we have a vector. Sometimes direction doesn't matter when we have a scalar. Now we're going to define three more quantities that are particular kinematics quantities. Distance, position, and displacement. We're going to define each of them. We're going to give you a symbol for each of these quantities. We're going to give you the units for each of these quantities. And then finally, we're going to establish whether they're vectors or scalars based on whether they require direction or not. Distance. Distance is the easy one to define, I think, isn't it? Distance is, quite simply, how far something moves. How far something moves. If I walk 10 meters, that's my distance traveled. If I drive 350 kilometers to Edmonton, that's my distance traveled. If I run 400 meters around the track outside, that's my distance traveled. How far I've traveled, right? Distance. The symbol for distance traveled would be a D with a little triangle in front of it. Does anybody know what that triangle means? Yep. Delta, yes. It's a Greek letter delta, which means change. Okay, so when you travel a certain distance, something's changed. Where you are has changed. Delta D means distance traveled. Okay, delta D, again, when I walk around the track or run around the track, is 400 meters. Delta D, when I go to Edmonton, is 350 kilometers. Now, there's lots of units that I can associate with distance, but there's one that's the most common. Kilometers, miles, light years is a unit for distance. What's the most common unit for distance that we're going to use? Meters, yes. Meters, and that's represented by a lowercase m. Now I want you to tell me whether it's a vector or a scalar. I run around the track, my distance is 400 meters. I go to Edmonton, my distance is 350 kilometers. Is it a vector or a scalar? I walk around the track, my distance traveled is 400 meters. Is it 400 meters north? It's 400 meters. It's a, heavy? It's a scalar. Good. It's a scalar. My position is where I am at one particular moment in time. Not how far I've gone, not how far I've traveled, not my change in anything. It's just where I am or where something is. Where something is at one particular moment in time. Its symbol isn't going to have a delta with it because it's not inferring any kind of change, any kind of movement. It's just going to be a D, almost. We'll fix that up in just a moment here. The units will be meters again, just like it was with distance. But position is a vector, because it's always important to know your position relative to something. Okay, relative to a reference point. My position relative to the wall is 3 meters to the north of the wall. My position relative to Calgary is 30 kilometers south of Calgary. My position relative to Banff is, I don't know, 150 kilometers, let's say, southeast of Banff. Okay. Position is a vector. It has to be measured relative to something, and it has to have a direction in it. Okay. Let's say that there's a first dance of the year we have. Have we had a dance yet this year? Have we? Back in the fall, did we have one? I don't know. Let's say we have a dance next week. Okay, and let's say Javi and Tara both go to the dance separately with their friends. Okay, and Javi's over on this side of the room with his buddies, and Tara's over on this side of the room with her buddies, and it's like a junior high dance all over again. Girls on one side, boys on the other side. And all of a sudden, Javi says to his buddies, you know, that girl over there, Tara, she's kind of cute. I think I might like to dance with her. And Tara's saying the same thing about Javi over on the other side of the room. Finally, they get together in the middle of the dance floor. They dance. They have a great time. And Javi says, you know, maybe we should go out sometime. Tara says, sure, that'd be great. I'd like that. And Javi says, how about Saturday? We'll go to a movie on Saturday night. Tara says, that's perfect. I'd love to go to a movie with you on Saturday night. And Javi says, well, where do you live? I'll pick you up at 6. Where do you live? And Tara says, oh, I live 7 kilometers west of 7 kilometers from Dairy Queen. I live 7 kilometers from the Dairy Queen. And Javi says, well, okay, perfect. I'll pick you up at 6. We'll see you then. Then Javi goes home and Saturday afternoon starts saying to himself, wait a second. She lives 7 kilometers from Dairy Queen. That doesn't help me much. She could live anywhere. So he phones her up and says, you know, Tara, I don't know if you did this on purpose, but when you gave me where you live, when you gave me your position, you didn't give me a direction. You gave me a scalar, not a vector. I need a direction. I need a vector for where you live. Okay? Tara says, oh, okay, I'm sorry. I didn't mean to do that, Javi. I live 7 kilometers west of Dairy Queen. So Javi goes and picks her up at 7. They have a great time and live happily ever after. Sometimes you need a direction. Okay, sometimes you don't. If you're measuring somebody's position, okay, Tara's position, you need direction. Direction matters. Okay, sometimes it doesn't, but when you're talking about position, direction matters. Does that make sense? Displacement is my change in position. Heavy starts off on Saturday afternoon at Dairy Queen because he likes to just hang out there. Then he goes and picks Tara up on Saturday night, 6 o'clock, 7 kilometers west of Okotoks, 7 kilometers west of the Dairy Queen. His initial position was 0. His final position was 7 kilometers west. His change in position was 7 kilometers west. Okay. Let's say he starts off 2 kilometers west of Dairy Queen. He goes to 7 kilometers west of Dairy Queen. What's his change in position now? 5 kilometers west. Right? He changed his position by 5 kilometers west. Does that make sense? Displacement is delta D because it's change in position. The units are meters. And because position is a vector, then displacement is a vector as well. Now, one final little thing before I give you a little thing to help you understand, really understand the difference between these three things. Right now, it looks like the symbol for distance and displacement are the same thing, right? They're not. We're going to put a little arrow on top of position here, half arrow, and a little half arrow on top of displacement. Whenever you have a vector, we need to put that arrow on top. Whenever you have a scalar, you don't. You leave it. Vectors have direction, so we draw a little arrow on top of the symbol to remind us of that. Scalars don't. Leave the arrow off. Okay, here's a little example here, okay? Right now, let's say the wall, remember we always want to measure something relative to something else, right? A reference point. Okay, my reference point is the wall. Okay, it's 0. Okay, I walk 1, 2, 3, 4, 5 steps. That's north, by the way. Okay, I walked 5 steps that way towards the north. What's my distance traveled there? 5 steps, right? 5 meters or 5 steps, right? We'll say it's meters. We'll say 1 step is 1 meter. Okay, so my distance traveled is 5 meters. What was my initial position back there at the wall? 0. What was my final position? 5 meters to the north, right? Because I walked to the north, 5 meters to the north. What's my change in position or my displacement there? 5 meters north, right? Easy so far? Okay, let's do it this way now. Let's say we walk 1, 2, 3, 4, 5 meters to the north, and then I turn around and walk 2 meters this way. 1, 2. What's my distance traveled during that entire trip? 7 meters, right? I walked 5 meters, then I walked 2 meters. We didn't pay any attention whatsoever to which direction I went, right? Because distance is a scalar. I walked 5, I walked 2, doesn't matter which direction. My total distance traveled was 7. What was my initial position? 0. What's my final position? 3 to the north. That make sense? Not 5 to the north or 7 to the north, because I went 5, then I came back 2. So now I'm 3 north of where I started. What's my displacement, my change in position there? 3 meters to the north, right? So in the first case, you saw how distance and displacement were exactly the same, 5 meters. Second case, you saw how distance and displacement were different. Why? Because I changed direction. As soon as I change direction, distance and displacement become 2 different values. And that's when it's really, really important to include that direction. All right, let's do an example here out of your textbook. First one, page 9. If you have your textbook downloaded, you can open it up and see a little bit of a more clear image of this, or otherwise you can just look on the board here. Example 1.1 says a traveler initially standing 1.5 meters to the right of the Inukshuk. So this guy is 1.5 meters to the right of the Inukshuk. That's where he starts, or she, I should say. She moves so that now she's 3.5 meters to the left of the Inukshuk. We want to find her displacement using directions and using plus and minus signs. Let's focus on this one first. What's her displacement? What's her displacement? She started right here. She ends up right here. She walked 1.5 meters to the left, and then she walked 3.5 meters to the left. What's her displacement? You guys know this, okay? You guys know this. What's her change in position? What's her displacement? Did she change direction? No. What's her distance traveled? How far did she go? 5 meters. Okay, if she didn't change direction, then her displacement will be the same number, but with the direction, right? So her displacement here will be 5 meters to the left. That make sense? We got that by saying, look, 1.5 meters to the left, 3.5 meters to the left gives me 5 meters to the left. That's her displacement. Now, let's do it using plus and minus signs. Let's define right as positive and left as negative. My displacement will be my final position minus my initial position, right? Displacement is change, a change in position. Final minus initial. My final position, if left is negative, is negative 3.5. I end up 3.5 meters to the left. What's my initial position? I'm going to subtract from that 1.5 to the right. So subtract positive 1.5. What do you get when you subtract those two numbers? What's negative 3.5 minus 1.5? Oh, come on. Take your calculators out if you can't subtract or add those or subtract them or whatever. What is it? I thought you were ready to say. Yeah, it's negative 5. My displacement is neg 5 meters. What does this negative mean? To the left, right? What was my answer when I did it the other way? 5 meters to the left. What's my answer when I do it this way? 5 meters to the left. Is that hard? Not crazy hard, I don't think. Okay, it takes a little bit of practice to kind of get the hang of it. That's why we're going to give you 3 questions for practice here. If you haven't written down, you don't have to write down the question here, but if you haven't written down the solution to the question, you should do that now. I'll give you a second to do that. And then I'll have you work on those 3 practice questions that are also on page 9 of your textbook. Okay, let's take a look at those 3 questions now, please. You see the answers at the bottom, but please try not to look at those answers before you actually solve the questions. Okay, let's get answers to them. See if your answers compare to what the answers that they gave, and then we'll take a look at these questions as a class if we have to, okay? All right, let's take a look at these now here. Question number 1 says, sprinting drills include running 40 meters to the north, walking 20 to the north, and then sprinting 100 to the north. What's the sprinter's displacement from the initial position? You know what? There's a couple ways that we can find displacement. Displacement is final position minus the initial position. If we have where the object is versus where the object was, then we're going to subtract them. If we already have displacements, in other words, we already have movements, then we're not going to subtract them, we're going to add them. Okay, we don't want to subtract 40 from 20 or 20 from 40 here. In this case, we're going to say delta D, the displacement, is equal to the first displacement, 40 meters, plus the second displacement, plus the third displacement. So when do we add and when do we subtract? When we have positions where something is, where something was, that's positions, we're going to subtract them. If we have how far the object has moved, that's displacements, we're going to add them. In this case, we're going to add them together. We're going to say north is positive, and that means the first one is 40.0 meters positive to the north, 20.0 meters positive to the north, and 100 meters positive to the north. We add those up, we end up getting 160 meters. And positive means north, so our answer is positive. Does that make sense? How many people got that? Good, good. 2, to perform a give and go, a basketball player fakes out the defense by moving 0.75 meters to the right, then 3.5 meters to the left. What's the player's displacement from the starting position? What do we have here? This basketball player moves to the right, then moves to the left. Are these positions or are these displacements? Are these where she is or how far she's gone? Is she 0.75 meters to the right of something, or has she moved 0.75 meters? Don't everybody speak at once. She's moved that far, right? Okay. She's moved this far as well. These are displacements. These aren't positions. We're not going to say 3.5 minus 0.75. We're going to say it's displacement plus displacement. 0.75 meters to the right plus delta D2 is negative 3.5. Why is it negative 3.5? Where does the negative come from? We're adding these two numbers together, but we're adding a negative value. Why? Because left is negative. If right is positive, left is negative. We add these two together, we end up getting negative 2.75 meters, which means 2.75 to the left. So even though you get the same thing, if you subtract 0.75 from 3.5, don't do that, because you got lucky on it if you did that. Okay, when we have two displacements, how far something's gone, we add them together. We just have to pay attention to positives and negatives. Finally, question number 3. While building a wall, a bricklayer sweeps cement back and forth. If she swings her hand back and forth a distance of 1.7 meters 4 times, what's the distance and what's the displacement her hand travels during that time? Distance is going to be distance 1 plus distance 2 plus distance 3 plus distance 4. Distance without the vector sign, right? Without the little half arrow. She sweeps at 1.7 meters plus 1.7 meters plus 1.7 meters plus 1.7 meters. Gives me a total distance traveled of 6.80 meters. Didn't matter whether it was to the right or to the left, because we were finding distance in that first question there. Now, in the second part of it, we're asked for displacement. Displacement is displacement 1 with the arrow over it, plus displacement 2, plus displacement 3, plus displacement 4. What's displacement 1? What's its value? Quick. Yep. Plus 1.70 meters. What's displacement 2? Minus 1.7 meters. Plus positive 1.7 meters plus negative 1.7 meters, right? Back and forth. Back and forth. Direction matters now because we're looking at displacement, whereas before when we were finding distance, the direction didn't matter. We add those together, we get 0 meters. Does that make sense? Who does track here in the spring? Who runs track? How far around is the track? Yeah, on the inner lane it's 400 meters. Good. Okay, when you run around that track once, what's your distance traveled? What's your distance traveled when you run around that track once? Right, 400 meters. What's your displacement when you run around that track once? 0. 0, because you end up where you started, right? Distance is how far you've traveled. Displacement is your change in position. And if you end up at the same position as you started at, your change in position is nothing. That's what we've got here, right? My distance is 6.8 because it doesn't matter what direction I went. My displacement was 0 because I ended up where I started. Okay? Here's your homework for tonight. First day homework? Wow. Mean teacher, eh? I want you to look at page 10. A few check and reflect questions, number 1 to 7 on page 10. Okay, page 10, number 1 to 7. You can spend the rest of the time today. Got about 5 minutes or so to work on those 7 questions. What you don't finish, please finish up tonight, okay? That's it for today.